So my name is Dino Daizovi. I'm the CTO and co-founder at Capsulate. Wanted to make sure to start off by saying that this is a group effort led by Brandon Edwards, the lead of our research team, including great work by Hrishikesh Kalburgi and Kent Ma. So this is a team effort, even though I'm the only one up on stage. I wanted to kind of tell you, a little bit about who I am and how I approach this. My background is in security assessment, and over my career, I've focused on different things. I started focusing on client-side exploitation kind of in the early 2000s, a little early, spent a lot of time on Apple technologies, including OS X and iOS. And over the last year and some change, kind of returned to my roots in Linux and taking a look at all the cool stuff that's going on with containers and orchestrated environments. And spent a lot of the last several months looking at the security of these environments, where they are today, because we've talked to a lot of people, and the adoption of these platforms is growing very, very rapidly. And a lot of us have been in security long enough to kind of know what happens when there is that sort of explosive growth. So let's talk about a little bit about what this is. So common misconception I hear from some people is, well, all this stuff is just about Docker containers, right? It's like, just that's all it is. I don't see what the big deal is. Well, not quite. There's a lot more to the story. And the metaphor that I normally use is of the modern assembly line and the era of mass production. So when people focus overly on just the container, which is just the artifact that you send to production, it's sort of like trying to understand the moving assembly line by the conveyor system. Yes, it's an important part, it's necessary, but it's not sufficient to get all the benefits of that efficiency. You need fixed stations, you need repeatable operations, you need the workload to move to the worker, and so on. And so when you're thinking about what the security of these modern environments, you need to look broader than just the container, and kind of explain a little bit more about what that means. The first way to understand this is to understand what people are trying to achieve out of it. And what they're trying to achieve is a element of scale and agility and velocity. And way to measure that velocity is by the number of deploys to production as a single variable that you can use to measure your efficiency. And that's called a fitness function. And good anecdote about this I found on a Medium post was a CTO or a CEO of a well-known tech company asked the CTO, "I've been asked to spend 15 minutes with President Obama to provide recommendations on how he should fix healthcare.gov. What would you say?" So how do you drill that down into one quick thing? And the CTO told him, "Suggest to President Obama that the team should deploy to production every day." And kind of the genius of this statement is that it's a forcing function to do everything else that you need to do for high quality engineering at high velocity. You cannot sustainably deploy to production every day without everything exploding unless you have all these other moving pieces and practices, and those kind of force you to do things like have small agile teams, independent containers, various patterns of composition in order to get that continuous delivery of software. And my thesis of when people are talking about DevOps, they're talking about containers, they're talking about a lot of some of the tools or techniques that are pieces of the picture. What they really want is continuous delivery. That is the real technology, that is the real enabler that any company adopting any of these technologies really wants, and everything else should be in support of that. And so what does it mean to have this continuous software delivery process? You need to adopt several key practices. Building a repeatable, automated, reliable software for releasing software. Automate absolutely everything. Everything must be version controlled. You should adopt practices where if something is painful, like previously deploying to production was a painful, painstaking operation. So what you do is you move it forward, bring the pain forward to make it more efficient. And so by deploying to production every day, you make it more seamless and build quality throughout the process. And the only time you mean done is when it's actually released to 100% of your users. It's rolled out. And make sure that instead of having this silos of development, operations, and security, everyone is involved in the delivery process. And I think as an industry, we're trying to figure out what it means for security to fit into this new way of doing engineering. So there's words, we haven't decided whether it's called SecOps, DevSecOps, DevSecOps, SecDevOps. OPSEC dev. We're kind of trying every permutation to explain what it means for security to not be an independent function that is a gatekeeper, rather a piece of the process of a continuous delivery pipeline, and focus on this continuous improvement. These are the things that when you adopt these practices, you can actually have continuous delivery. And orchestration and containers are very key components of this. So the container is just the software artifact sent to production. It's focusing too much on it is like looking at the desktop, the PC revolution and personal computing and thinking it's all about like the COM file. It's like, yeah, the basic executable is a piece of the puzzle, but it's really a whole bunch of other things. But all a container really is it's a reusable, composable, and suitably abstracted from the environment piece of software. And it allows you to just have a reproducible artifact that you can develop, test, and ship to production and keep it all in version control. When you're using these at scale, you need an orchestration system to schedule their operation. And dynamically schedule them to nodes, and also automatically handle rollouts, failover, scaling. And this is actually one of the key points about orchestration systems, is that they are an ideal place to implement a lot of the security functionality that you need in your production environment, because they are the software fabric around everything. And so what we'll see in a lot of these environments is pushing more and more security into that, so that you don't have to implement security in every single application, which is tedious and also very painstaking. So my security thesis when I started this research was how I approach a lot of things. I think attackers are always looking for the new frontier to exploit, while defenders are still fighting the last war. And so how I saw this pattern manifest itself in this ecosystem were things like an excessive amount of focus from security practitioners on OS level container escapes, focusing on kernel vulnerabilities, focusing on these things that kind of impedes looking a little broader and seeing just how exposed the rest of the cluster level APIs are from inside those containers. Because just looking at those escapes is like just running a Docker container on a single workstation, and that's pretty much only in development, not really where it matters as in production. Another corollary I had going into this was that when you only focus on the scope of an individual node, like you're thinking about, okay, so how do I escalate privileges? How do I install a rootkit on a particular node in the cluster? You also miss what you can do at the entire cluster level. Because one of the patterns of these orchestrated environments is that nodes can come and go. They're torn up, torn down, and a lot of companies that are using these type of environments already, they don't measure uptime in terms of how long the systems have been up. They don't see that as a good thing. They want to measure reverse uptime and basically take that number down. They want to have systems be short-lived, ephemeral, and have that pattern kind of throughout every stack, or through every layer of their stack. And the third thing I saw was that overly focusing on immutability of the containers themselves and even the operating systems on the nodes misses a lot of weaknesses in where the mutability of the cluster level state allows all the types of persistence that an attacker would want. So how I normally go about things is I start with an attack graph to kind of figure out what the choices an attacker would make and why in different environments. So we start with the assumption of an attacker obtains remote code execution in a container in a cluster in one of these environments. So that I'll just use shell shock as a high profile example, but one of the things I've noticed over the last few years is that the prevalence of remote command injection vulnerabilities in a lot of popular Linux software is pretty surprising. And whereas on like the Windows desktop world, we're talking about vulnerabilities that involve insane levels of heap manipulation and arcane low-level techniques, a lot of the attacks that are succeeding at a pretty impactful scale against production environments are just shell meta character injection in the right place. So shell shock, you just put it in a environment variable, it gets passed to bash. Image tragic, you have an image conversion routine that shells out similar vulnerabilities in Go script. It's I think as people start looking more at this, you're going to see a lot more as a problem. And so especially as we are rapidly taking less mature software, putting it in containers, exposing it to the internet, and moving it through that cycle. So this is my starting point. Kind of the traditional route of the traditional strategy is starting at I have node, looking for a privilege escalation on the node. Get out of the container, get root, and then see if I can persist on the cluster. However, that's not as useful as looking at other things where we can say, all right, well, why don't we, instead of that, look for lateral movement opportunities within the cluster directly. And from there, we can look for privilege escalation within the, at the cluster level, and then cluster level persistence. And this is possible from, just direct container remote code execution, privileged access to the node, or somewhere that you've moved laterally to. And it sort of shows that that's the area that I think is the most important to focus on, is from different levels of access, how can you escalate cluster level privileges? So let's talk about a few of the various alternatives for orchestration systems. I'll start with Docker Swarm. The service model for Docker Swarm is, I would call it the least complex of the leading orchestration systems. It is largely Docker Compose as a platform. And how it works is you have a service that is defined of a container, one or more containers, and Swarm will schedule and scale it across available nodes as tasks. They will farm it out and manage a configured number of replicas so that if one goes down, another one is automatically restarted, or you can also auto-scale the number of replicas as well. How this is implemented is through Docker Swarm or Swarm mode of Docker. And there's two types of nodes in this configuration. There are managers and there are workers, much like our daily lives. And the managers are all in a Raft consensus group. So there's a distributed key value store, essentially. This is a pattern you'll see on all these systems. A distributed key value store, and kind of the masters and the managers of the orchestration use that to maintain a quorum and the actual cluster state among themselves. And so you'll always want a odd number of manager nodes, regardless of whether you're using Raft or whether you're using Paxos. But this makes sure that the cluster itself is consistent, even if there's network issues. All the workers communicate over a gossip network, so they can primarily to manage the overlay virtual network across them. And the one thing that you'll also notice, and kind of slightly different than traditional virtual machine-based network architectures, where there's a very strict separation between control plane and data plane, a lot of the orchestrators today combine them on the same network fabric, and they'll have overlay networks for the data plane, but they'll go over the same links, and they'll just use TLS and various other encrypted protocols to protect the control plane traffic. So Swarm actually does a really good job at this. They spent a lot of time on the security model and the security features, and they're sort of the gold standard of orchestration security today. And how they work is the manager is a X509 CA. The manager's form X509 CA for the entire swarm, and they use this to implement mutual authentication between all the control components, between nodes, between managers as well. And the data plane traffic by default is unencrypted. However, you can optionally encrypt it, and IPsec tunnels will be created between all the service dependencies of your workload. So a container will only have access to the links that you have declared. So an app container will only have access to a database that you've declared, not access to over the network to talk to the managers or anything else. And another key aspect of how Swarm model is implemented is that it is a least privileged design. The containers themselves are always considered by default untrusted. The nodes themselves that they run upon are by default considered untrusted. And they are only given the minimal amount of information to do their job. So it's a kind of it's a pretty good model. In addition, so this interacts most concretely with secrets. where secrets are, what they sound like, objects that are defined to like be passwords to whatever an app will need, but they're encrypted at rest throughout all of Docker Swarm, and they're only sent to nodes that have a job that needs them, rather than making them accessible to the entire cluster. So, if we look at what would something like shell shock being exploited look like on Docker Swarm? It's pretty uninteresting, because you get a shell in the container. The attack surface is essentially all you get from a highly constrained container on a single system, and there's not a lot you can do. There's no API you can talk to. There's no there's just not a lot of avenues for lateral movement or anything like that. So the attacks that you want to do are largely scanning the data plane for other accessible services or that you have access to, and trying to escalate privileges through there, or traditional operating system level container escapes. And there's sort of a lot of other research being done there, so that was something that, while it's important and necessary, not the focus of this talk. But one aspect that I did want to highlight about how Swarm works is, in order to make it easy to use and allow nodes, especially in an environment like a cloud environment where you want to scale up and scale down seamlessly, they support joining the Swarm with a single cryptographic token. So this join token automatically authorizes the node to join the Swarm, and doesn't require an explicit approval or confirmation for each new node, and the tokens themselves are not consumed. They're easy to rotate, they're easy to change and disable, and they're only needed when the node joins the Swarm, never after the fact. But they have a very regular format, so they're easy to find in source code, which is a plus and a minus, and easy to find in memory as well. So if an attacker is able to escalate privileges outside of the container and gain root on the underlying host, there's actually stuff they can do against Swarm. And so a lot of the attacks go back to kind of 1990s style hacking with ARP spoofing and denial of service at the network level. And what you can do is disable the network connectivity to legitimate worker nodes and essentially hijack their IP address. However, you should note that you don't actually get their cryptographic identity. It just looks like a new node to Swarm. It looks like a new node with the same IP address, because the cryptographic identity is assigned through a certificate that is granted through a CSR when you present the join token. So by reusing the join token, you're just getting a new CSR while blocking if you're using the same IP address, you're blocking the legitimate node. And what this lets you do is you can proceed to, by blocking legitimate nodes and taking up all the kind of the subnet, you will be assigned all available services, all the apps running on the cluster, because the Docker Swarm will notice that they're no longer reachable, they need to be rescheduled, and so they'll schedule them all on your rogue node. So let's see what that looks like, and make sure this works. So we have, we're showing both systems. Right now we're on the manager, showing kind of the layout of the environment. We have 2 workers and 1 manager, a few database services running on the Swarm, and we can see that they're all scheduled to run, and they're running right now. So now we're switching over to worker 2, assuming that we have escalated privileges broken out of the container, and what we're going to do is try and find this join token. And the easiest way to do it is, if you have root access already, is scrape it out of memory from the Docker process. It's regular string, it's easy to find, and it is not scrubbed from memory currently. So if the system is still up after having joined the Swarm, you can recover it pretty easily. And our attack uses that join token and talks to the manager and implements this, where we ARP spoof the legitimate nodes to the manager, and so that they can't be assigned new jobs. We can take all the available identities and get all the services reassigned into our rogue nodes. And once that's done, we will get the secrets for those services sent to us. And so we can get all the database credentials, we can get all of the whatever other secrets are are included in the, for those jobs. So I don't want to see that again. There are several ways to mitigate this. First is what I mentioned earlier. The join tokens are incredibly easy to rotate, so they should be rotated frequently. Docker recommends every 6 months, or on events such as disclosing it through checking into version control. Pretty easy to run like Git hooks that can actually detect this, or you can use the GitHub API to find that through your repos. So you can write a job that will search for this, and anytime that happens, boom, just expire the token. Or if you have other reason to believe that a swarm node may have been compromised. If you wish, or you can also rotate it if you want to guarantee that no new nodes can join the system. However, when you do this, you're preventing the swarm from auto-scaling up new nodes. And if you're using like an auto-scaling group in something like AWS, this might not be desirable. Or minimum at every 6 months. One of the kind of most important things to do, however, to mitigate this are to use node and service labels to segregate sensitive services. So Swarm lets you designate certain services as sensitive, or just using labels, and nodes as sensitive as well. And this is all kept in the manager state, and even a rogue node cannot give itself a label. So when we perform an attack like this, we will be essentially an unlabeled node, and so we'll only get access to unlabeled services. So this requires that you go through and actually do all that. So that's Swarm. Let's talk about Kubernetes. So Kubernetes is one of the largest and most active open source projects right now. It's pretty startling how active it is and how fast it's growing. This chart I took from a blog post from the Cloud Native Computing Foundation. Shows on the left logarithmic PRs and issues, and going to the right going up is PRs, going to the right is the number of commits. So you can see that even though Kubernetes is a relatively young project, has a massive amount of activity in PRs and issues, and it's moving quickly. It's already moving up, moving quickly to the right towards Linux and Chromium. So there's a lot of activity, and it's actually pretty remarkable how many large companies have full-time engineers contributing to this project, and you can kind of see where all this is going. So while Swarm was easy to understand, Kubernetes is a bit more complicated, and the complexity of it is actually a lot of the benefits, because for a lot of modern services, the service model that is implemented in Docker Swarm may not be sufficient. So the architecture, let's go quickly over the architecture of Kubernetes. It starts with, you have again, like a central distributed key value store. In Kubernetes, this is called etcd, and this is essentially the backing store for all state for the cluster. In front of that, you have API servers that implement an interface to the scheduling and operations of the cluster. And each node runs an entity called a kubelet. Kubelet is it presents its own API locally, but it also, or that the Kubernetes master will speak to, and is responsible for scheduling and running actual containers on the node. And in Kubernetes, these are called pods. You don't run a single container, you run a pod that has kind of forms the Linux namespace, and multiple containers run concurrently in it. And Kubernetes is a very abstract architecture. There's multiple plugins to implement various features, so you have a declarative API saying, I have this network policy that I want to happen, and there's multiple plugins that you can use to implement that. So you'll have things like Weave, Calico, and so on to implement these policies that you've declared. I'll go briefly over some of the objects that kind of show the scope of what Kubernetes actually permits you to do. So we have nodes and containers. Those are pretty obvious. I mentioned pods. But we also have entities like a namespace. We have multiple namespaces so that you can partition out your cluster to different groups and different teams using the same hardware. And they're not able to and if you configure things correctly, not able to see or interact with entities outside of their namespace. So what some people or some environments would use something like this for is to have their production, their development, test staging and production environments on the same hardware, however in separate namespaces, so that you can achieve a lower cost and greater scale doing that, and just using namespaces to isolate rather than separate hardware. And you can also apply the resource constraints to a namespace, so you can make sure that jobs that the data science team is doing that might be CPU heavy are not interfering with the latency sensitive production jobs serving for internet services. Pods all communicate internally through what is called a service. Service is a virtual IP that allows communication between pods. So that's how you'll find each other and communicate. Replication controllers are just one of the many other metapod abstractions that let you scale services up and down. Ingress is kind of my favorite, which lets you route HTTP requests based on path and host to arbitrary services and pods. So you can have one host name that gets basically farmed out to various things inside your cluster. This is relatively new in Kubernetes, but it gives you a lot of functionality that is really useful. So the security mechanisms of Kubernetes are being very rapidly developed, and it's just about most things that I'm going to talk about are are either alpha or beta or less than a month old. So the first most important one that if you don't have your entire cluster is essentially one security domain, regardless of the user permissions inside a container. If you follow like the Docker hardening guidelines, they don't really matter when you have no RBAC enabled on a Kubernetes cluster. Only in Kubernetes 1.6 and greater is it enabled by default. However, a lot of installations and guides don't work with it enabled. So if you're trying to install packages from things like Helm, they may not work with RBAC, so a lot of people are still turning it off. Another key component that you want to make sure you have enabled is the pod security policy admission controller. So this is the entity that runs on the master nodes that will enforce security requirements like not letting anyone execute a privileged node. And one of the things you can declare in Kubernetes is I want to run a privileged pod. I want to run this pod, but I want to give it full host privileges, or I want to give it access to the host network. All these things are disabled by the pod security policy, and this is something that was contributed to Kubernetes, developed first in Red Hat's OpenShift, and then contributed upstream to open source Kubernetes. And one thing I wanted to clarify is that most of the stuff I'm talking about is all open source Kubernetes, and there are commercial distributions like Red Hat's OpenShift, CoreOS Tectonic, Google Container Engine, but there's a lot of activity happening in the open source distributions and installers that are describing them as production grade, production ready, that aren't as explicit about how many of the security features aren't enabled or in existence that you would want if you don't want your entire cluster to be one security domain. So the other one is the node restriction admission controller. This is very, very new. I think it's alpha right now, prevents kubelets from obtaining resources for pods that are not scheduled onto them, similar to Docker's least privilege architecture. And there's also network policy resources, which allows you to apply isolation and segmentation so that your workloads can be segregated. However, one thing that I would point out is that this doesn't actually fully let you control segregation from the control plane. So a lot of the kubelet, the master API, are not actually restricted by these. So let's go into the attack surface if you get code execution in a pod in a Kubernetes environment. The most surprising thing that I noticed and was pretty surprised by, every pod by default has access to a service account token mounted into the pod. So even if you don't build this into your container, it's injected by the orchestrator, and this token gives even unprivileged users inside the container cluster level privileges, and without RBAC, that's cluster level root. Token is word readable. And the service account lets you do just about anything, like launch new pods, launch new privileged pods, and you can do all this. The other model that is kind of unique to Kubernetes is that the service model is implemented, like the service virtual IPs and load balancing are implemented on the node, not in some central infrastructure. So it makes it really fast to scan service VIPs because they're just going through like local IP tables configurations. So if you want to do that, it's pretty easy to find what the service subnet is. You'll have an environment variable, Kubernetes service host, that is a service IP that gives you the IP address of the Kubernetes master API. And so you can just port scan the subnet for well-known ports, look for services to actually interact with. Another way you can do this is just looking through service names in kubedns. kubedns is the cluster DNS service that allows service discovery. So you can query for common service name, .namespace.svc cluster.local. So for instance, if you didn't have the IP address for that environment variable, you could just do a DNS lookup through kubernetes.default. Default is the default namespace, svc cluster.local to get the Kubernetes API servers. So let's see what shell shock looks like if you exploit it on Kubernetes. So exploit shell shock in a vulnerable container. Next thing an attacker will do is download some tools. So one thing that also might be going through your mind is how much this sounds like the common pattern of attacking a Windows desktop. You get initial access and then download something like Mimikatz and then lateral privilege escalation. These same patterns are actually available at the cluster level, so we're going to kind of go through that same flow. So download a common tool, not a piece of malware, just kubectl, the standard tool to interface with the API, and use the service account token to authenticate to the API servers. And you can just escalate privileges through calls to the Kubernetes API or scan for something useful. So I'm picking on one particular service here, the Tiller deployment service. I'll talk a little bit more about what Tiller is in a minute. So let's look at the environment that you get from a shell inside the container that's specific to Kubernetes. You have all these environment variables giving you the API server, which I mentioned before. If you look at the mount points, you can see that the secrets are typically mounted into the file system, and by default that service account token is mounted into the container. And using that token with a downloaded kubectl or some other client, we can start interfacing with the API. We can talk to list the nodes, and that'll verify that we have some level of access. And then we can see if we have more access by launching a privileged pod. So the example I give is just a command line invocation that will create a new pod and of running the BusyBox container. Why BusyBox? Because it's small, it's quick to download, and has a lot of useful shell tools. And I'm giving it a security context of privileged equals true. So just means we have root on the node from this one call to the API. And if you don't have RBAC enabled on your cluster, or you're essentially running Kubernetes below 1.6, this is what is possible from just about any container. So assuming that is fixed, that you're running either a commercial distribution of Kubernetes that has addressed this, you've addressed it yourself, or something else, there's a lot of other lack of authentication inside the cluster. So one popular way to install software in Kubernetes environments today is called Helm. It is the official package manager for Kubernetes, and it's actually really cool because what it lets you do is have essentially an app store for your cluster. So you can install complicated infrastructure such as Spark. You can install Kafka. You can install Cassandra. Data center applications that traditionally require entire teams to operate can now be installed with like a click of a button, and there's software operators inside Kubernetes that will even scale them automatically for you. So it's pretty awesome, but they just haven't implemented any access control yet, or it's just not enabled. There's an open GitHub ticket to actually enable it. So if you have a shell in a cluster, you can just look for what's called the Tiller deploy service, because the way that Helm is built is you have the Helm command line, and in order to start using it, you need to deploy a privileged service inside your cluster to actually perform the package installations. That's called Tiller. So if you do a kube DNS lookup for tiller deploy.kube-system, so kube-system is the system namespace. The default port for it is 44134, and you can connect to it. And so there's not a good command line client for it, so I just wrote a quick one. It's a gRPC interface. All the code is on GitHub, so it's just very easy to write stuff to interact with if you know how to write gRPC clients. And then you can do everything the Helm command line can do from inside the cluster. You can install packages, query them, uninstall them. So because it runs with privilege and all the packages that you're installing have to have privileges, even if you have something like a pod admission controller or a pod security policy, they're likely going to have to enable Tiller to be able to bypass that. So you can just talk to Tiller instead. So kind of drilling down some of my key recommendations for securing Kubernetes environments. First and foremost, make sure that RBAC is enabled and configured appropriately. That's sort of one of those loaded statements of like, just turn on security. There's actually a lot that goes into this because there's still a bunch of sharp edges in the security policies of Kubernetes objects. So for instance, if you have if you have access to write into a namespace, and even if you have a pod security controller that doesn't allow you to create privileged pods, but a privileged pod is already running, you can create services or you have a pod that's running on the host network, you can create services to route onto the host network. And once you have, host network access, privilege escalation is pretty easy through a variety of ways. So right now, even with RBAC enabled, having write access to a namespace with any privileged pods is it's not quite game over, but it's one step away. You absolutely need to have a pod security policy configured if you are letting any jobs like automatic or continuous deployment jobs deploy to the cluster, or if you give developers access to deploy to the cluster. A pod security policy is crucial. Also, something that I was surprised to see disabled more than I'd expect was the kubelet and Kubernetes Masters APIs not having TLS certificate authentication enabled. And that just basically gives you root to the cluster. And even some open source kind of installers for Kubernetes, they would not enable this on etcd. So if they enabled certificate authentication on the API servers, however, you can connect to the etcd key value store, which if you can connect and there's no cert-based auth enabled, you just have full access to read and write the state directly and escalate privileges that way. So that's pretty simple stuff that you need to make sure is all there. Also, the node authorizer, which is beta right now, just released to Google Container Engine, I think this month, can restrict kubelet's access to resources that are not scheduled or not belonging to a pod scheduled to them. And also there are multiple network policy providers such as Cilium, Calico, that you can use to implement the network policy API so that you can apply access control lists to services so that not every service is globally accessible through the cluster. This is, if you're noticing that there's this slide is a lot of work to implement in your environment. That's sort of where open source Kubernetes is today. It feels a little bit like the early days of Linux, but if everyone was root, on your system for the first several years, and they're like, yeah, we'll implement that security model a little later. So, but it exists. It just takes a lot of bootstrapping or using a commercial version of Kubernetes that actually has it all done for you. So let's talk about I'll call it the quiet giant. This is DCOS and Mesos. It's the environment that you don't really hear much about, but it's the only one that can scale to hundreds of thousands of nodes. So it's in some very large environments. It's a similar pattern to the other systems. We have a distributed key value store. This one is Zookeeper, which is used for Kafka and a variety of other internet scale services. And it's a bit more complicated than Kubernetes in that you have two levels of scheduling implemented by, first you have Mesos, which is a two-level scheduler, and then you have what are called frameworks on top of it that can schedule cluster resources to some other way. If you're running like a large Cassandra cluster, you might be using direct Mesos, but a lot of people use Marathon to schedule containers, and there's a massive suite of stuff. They also have an App Store-like thing called Universe, but one thing that is pretty explicit on the Mesosphere website is that batteries are not included. The security features exist only in the commercial DCOS, and there's, by default, containers run on the host plane, on the host network, so any container schedule has full access to the host. You can connect to a lot of services right there, and I've seen a lot of configurations where Zookeeper has no authentication enabled, so let's kind of look at what Shellshock looks like there. The container environment, you can get the host IPs pretty easily of the control plane, and you can actually talk to it directly and dump the state and get the authentication settings. And in this example, you can see that there's no authentication actually enabled or required. So that means we can launch jobs on the node without authentication. We can also connect to the master and do the same. But sort of the most fun one is just talking directly to Zookeeper. So you can, inside the cluster, all the Zookeeper instances are, you can look up through Mesos DNS at ZK1 through ZK5. And usually the Zookeeper client is a large Java package, but I just wrote one in Go, and you can just talk directly to it and crawl through it and get things like the auth token secret, which is used for all of the JWT tokens, and then from there you can just mint your own authorization tokens and do whatever you want forever. So it's cool. So the tools that I made to do this, I couldn't really think of a good name, so going with Crispy Tribble for now. It is a container image for assessing orchestrated environments. You just launch it. It has a built-in Go SSH server, so you can just SSH in, see that kind of that kind of raw environment, and has a variety of tools for inspecting what is going on inside the cluster. So you have kubectl, etcd ctl, two small command line tools I wrote called just one called Tiller and one called ZK to talk to these services and do with it, or basically just perform operations on them and when there's no authentication required. And background on the name, if you just create a project on GitHub, it says, don't have a name, not feeling inspired, try this one. And it said Crispy Tribble, and I was like, all right, that'll work. So kind of the high-level takeaways I want people to kind of remember from this is that sadly, the open source distributions of Kubernetes and Mesos and DCOS don't have all the security features enabled. They don't have them implemented in some cases. And so if you're not prepared to go through a lot of work and a lot of learning curve, like I spent probably 2 to 3 months learning Kubernetes this year because I actually ran our Kubernetes cluster for the first part of the year. There's a lot you're going to have to get working to have reasonable level of security. And that just means not having root within every container on the entire cluster. But they're moving pretty quickly to have all these features. Managing API authentication, control plane and data plane separation is actually a little farther out. Actual workload isolation, S2S authentication and authorization, and a zero trust networking model, so that even if the control plane or data plane physical networks are compromised, it's not an issue, and also a least privilege orchestration model. They're moving pretty quickly to this, but it's while a lot of the open source systems will say they're production ready, production grade, make sure all of these are enabled in it. Otherwise, you're better off with the commercial version so far. But one of the things that'll be interesting for us as a security industry to watch is that what I'm seeing in kind of the desktop ecosystem is a lot more solidification of and restriction of what's possible on devices as everything becomes like a mobile device. It's firmware, you can install apps, that's all you can do. In order for people to just move and implement functionality, it has to go somewhere. And so I think what's going to happen is we're going to see all that flexibility go onto the into people's data centers, because environments like Kubernetes and like App Store-like installation of complicated infrastructure will remove the barriers to entry, and we're going to see a Android ecosystem-like scenario in data centers because of this, and it'll be interesting. And one of the things that I'm actually seeing kind of fascinated by is that the growth of the cloud is actually massively propelling the use of Linux, because it is the native operating system kernel of the cloud, and it's pretty cool to see that. So that's all I have. Thank you everyone for your attention. I have 2 minutes, 3 minutes for questions. 4.